Tonight's lecture is 11.3 through 11.5 in your textbook, Properties of Liquids and Phase Changes, and we're also going to throw in a tiny little bit of, um, vapor pressure as well. So let's get right to it here. So we're going to be talking about, like I said, 11.3 properties of the liquids, and so we'll first start talking about. We know already liquids have the ability to flow. They'll take the shape of the container, things like that. A few things that are going to come up in this section. One of them is the idea of viscosity, and you hear viscosity talked about a lot with respect to things like motor oil. And this is going to be the resistance of a liquid to flow, defined as viscosity. Um, Basically, the more viscosity something has, the more resistance to flow it has, meaning it doesn't want to pour. A couple examples: water or alcohol would have a very low viscosity. They're very easy to pour. You take a glass of water, you dump it, it's just going to pour right out. No big deal. Compare that to like maybe some pancake syrup or some motor oil. These are going to pour a lot slower than water or alcohol might pour. So we would say that they both have greater viscosity. And if we're looking at substances that are very similar, it tends to increase with molecular mass. Basically, the reason why is you're going to have more surface area, you're going to have more intermolecular forces, as we talked about in the other night's lecture. More electrons, possibly that squishiness that we talked about, polarizability. Okay. So along these lines, it's a very similar concept, and these are all based on intermolecular forces of molecules. There's the idea of surface tension. And this is going to be the attraction of a molecule to create kind of like a skin on a liquid. And let me scroll down here a little bit, and I'm going to give you a couple examples here. Water molecules are going to have hydrogen bonding, as we know. So we have one water molecule that is going to be it is going to have a force of attraction to another water molecule due to these water molecules being polar. And that water molecule will then have a force of attraction to another water molecule, all due to the polarity of these water molecules. Now, enough of these water molecules get together, and we're going to have this sort of skin, the surface tension on water. And many of us have done that experiment in a lower science class where we took a penny, and this would be like a side shot of a penny, and we counted how many drops of water we could put on that penny, and we found out that we could put quite many drops of water on that penny. Let's say these are the drops of water all coalescing together, and you notice that these drops of water are hanging over the side of the penny without breaking and falling. And the reason for that is that surface tension, that attraction from these water molecules that are holding on to each other. That's what's going on here. And I have a quick little video I do want to show you. This is a real short video, but it's going to show some neat things on surface tension. Now, in this video, what they've done is they have a high-speed camera, and they are dropping water droplets onto the surface of a water, and you're going to kind of see what's going to happen with some of these, especially how we see water droplets bouncing off of the surface of a glass of water. And there's one just kind of sitting there on the surface before it kind of sinks in there, and it really has to do with the surface tension of water, those intermolecular forces. That's hydrogen bonds that are holding one water molecule together. And there's another one, the little smaller one, that just kind of bounces right on the surface up and down and loses a few water molecules as it goes along. So that's a video just showing you that surface area of water. And I did say surface area of water. I did mean to say surface tension of water, not surface area. Okay, and a couple more terms that we should be kind of familiar with respect to all these intermolecular forces. And one of these terms is the term cohesive. And what we mean by a cohesive force is going to be when we have similar molecules having a force of attraction between them. And we've talked about this as an intermolecular force. This is called a cohesive force. Now, something also can happen as well is when we have molecules, we'll have a force of attraction for the surface of the container that they're put in. Whenever this happens, we call this an adhesive force. So cohesive is when molecule is attracted to molecule. Adhesive is when a molecule is attracted to um, uh, the surface of a container that they're placed in. And a good example of this is the idea of a meniscus. And we've talked about this in pretty much any chemistry class. If we have a graduated cylinder, and this is a poorly drawn graduated cylinder, and we put some liquid in there, oftentimes a real small glass graduated cylinder, we're going to have this dip down on the surface level, and we call that a meniscus. And we're always told, rule of thumb is to read the bottom of the meniscus as your measurement. Well, the reason a meniscus exists is because, let's say in water, and in this picture I have right here, water is on the left. Water is going to have a concave meniscus, meaning this is going to dip down in the middle and then kind of climb up the side of the glass test tube, as you see there. And it's because the adhesive forces between the water and the glass are greater than the cohesive forces between the water and the water. So we already know that water and water do have a nice hydrogen bond going on, and that's good. But the water is also attracted to the glass, which causes that water to try to sort of climb up the glass, this force of attraction, and that's why we get a little meniscus and a dip down in the middle for water. Now, on the right-hand side here of this picture, we have mercury. Some mercury, which is a liquid at room temperature. And you notice what's happening with the mercury is it's got a convex. Mercury has a convex meniscus. And so what's happening with mercury is the mercury atoms have a greater force of attraction. Their adhesive forces are greater than the cohesive forces that are going on between the mercury and the glass. Okay? So that's the difference between water and mercury with respect to this meniscus. Okay. A couple more things that we want to talk about before we change the subject a little bit here. And let's talk about capillary action. A capillary action can be defined as the rise of a liquid up a very narrow tube due to adhesive forces of the liquid of a tube. And this is something that occurs in real small tubing. We call that tubing capillary tubing, which is really, really fine capillary tubing that, let's say, has it's a glass tubing that has a real small opening in it. And so if you dip this in liquid, it will actually pull the liquid right up the tubing due to the adhesive forces, those forces between the water molecule and the glass. And this is also the idea of how really tall trees can get water from the root systems all the way up to the tip of the trees where the leaves are up there. Capillary action is moving things along. And we'll leave it at that. Next thing I want to talk about real quickly is in 11.4, there is a lot of information about phase changes, but really what we want to talk about is the energy of a system. So what we have here on this graph, just to kind of analyze this graph, is increasing energy. We have increasing kinetic energy. These molecules are moving faster. And so if we are a solid, let's say we're ice, down here, ice, which is, we know, solid water. If we want to get ice to melt, we've got to heat it up, and that's called melting. In chemistry, we also like to call that fusion. So sometimes the amount of heat will be called the heat of fusion, the amount of heat that's required to turn a solid into a liquid. And sometimes we'll call that delta H, change in heat, or enthalpy of fusion. We add more heat, and we can get a liquid to turn into a gas. Call that vaporization, and oftentimes we call that delta H of vaporization, or the enthalpy, the change in heat, constant pressure of vaporization to get to a gas. And we know these gas molecules up here have a very high kinetic energy. They're moving very rapidly. Now, we can get these guys to condense by removing the heat, exothermic reaction, so the condensation is occurring, going back to a liquid, and then we can remove the heat further and get it to go back to a solid as well. Now, a couple things to recognize and note here as well. If we do have a solid, we can make it go directly from a solid form to a gaseous form over here, and we do that by what's called sublimation. Sublimation is skipping the liquid step. And a good example of sublimation would be dry ice, CO2 in the solid form. And this goes directly to CO2 in the gaseous form when it sublimes. And the opposite of that would be deposition, going directly from a gaseous form to a solid form, which would never going through the liquid phase. Okay. Now the last idea that I want to talk about tonight is vapor pressure. Now, we can define vapor pressure as the pressure exerted by molecules of a liquid that have evaporated and now are above the liquid. Now remember, anytime you have a gaseous molecule and it starts running into the sides of a container, we're going to create a pressure. And pressure is going to be, vapor pressure is going to be that pressure above a liquid. So let's look at this little diagram here, and we're going to start from the left here. We'll start over here on number 1, and we have our initial conditions. What we've got set up here is we've got some liquid water here, and we just put it in there. It hasn't started evaporating at all, and we're going to kind of pretend there's nothing up here in this vicinity. There's nothing there yet. It's just evacuated. Also, over here we've got this closed off. We've got it connected to mercury in a tube, a U-tube, and of course it's not really super accurate, because if this, we would have that little meniscus that would look like that and look like that. We know that, but that's okay. Now, so what's going to happen here, or what's going on here? Well, first off, the water molecules that we have in our liquid water here have some intermolecular force. And we know those intermolecular forces now as hydrogen bonds. And they also have London dispersion forces, because everybody's got that. And that's what's holding those guys together. Even those molecules, those water molecules, are moving around together, but that's kind of what's holding them in the liquid phase. And let's say this is just at regular, maybe room temperature. Now, some of those molecules, and we're over here in number 2, some of these molecules have enough kinetic energy. And if they have enough kinetic energy, they can overcome the intermolecular forces, and they can break free. So you see some of these breaking free, that right there at the surface, there's one there, and there's one there, there's one there. They're breaking free. And now we got these guys up here, and these guys are bouncing around, and they're bouncing around, and some of them have even gone into this little tube and are bouncing around inside this tube. And you've noticed, hopefully you can see, that the mercury level has risen on the right-hand side and has dropped on the left-hand side, because the vapor pressure is increasing. So we have increasing vapor pressures pushing down on the mercury and pushing up, pushing down here and pushing up over here. Okay. Something also that we should note that's really important is, look right over here. We've got a water molecule that's re-entered the water. Now that's going to happen sometimes. Now over here on our third diagram, our vapor pressure has become constant. And so what that means is we have an equilibrium. An equilibrium has occurred. And really what an equilibrium means is we have equal rates, meaning how fast, of evaporation, and we can call it condensation. So essentially what it means is, and it's kind of, I like this diagram, is we have equal rates. There's water molecules leaving the water, but then notice there's also a couple of them going back into the water. Now that's going to stay constant. We also notice that our mercury levels have gone down on the left and they've gone up on the right. There's our vapor pressure. Okay, once this becomes constant, there's our vapor pressure, which is the difference between those two. And that's really what vapor pressure is all about. Just the pressure of a gas above a liquid caused by evaporation. Now, this next thing is we're talking about vapor pressure and how it relates to boiling point. Because vapor pressure really is, boiling point really is when vapor pressure is equal to the atmospheric pressure. And that's when something starts to boil, vapor pressure. So a couple of things that we need to know. So that's our boiling point. So when vapor pressure is equal to atmospheric pressure, and it's going to be the temperature at which something boils as well. So let's look at what's going on here. We have a normal boiling point, and that's just going to be 760 millimeters of mercury, or 1 atm. That's just our normal conditions. And the question that's being asked down here is, how does increasing or decreasing pressure affect the boiling point of a substance? Okay. So what I'm going to do first is let's look at water here. Water's illustrated by the blue line. And so we can see at normal vapor pressure, or normal pressure, 1 atm. 1 atm is right there. Oops. Right there. Our water is going to boil at 100 degrees Celsius. If we decrease the pressure, let's say we decrease the pressure down to, I don't know, 600 millimeters of mercury, then water is going to boil at a lower temperature. It might boil at, say, 90 degrees Celsius. So it takes more. And we've got to remember that once water gets to its boiling point, and as long as pressure stays the same, it doesn't get any hotter. As long as we could add more heat, it just stays at the same temperature. If we wanted to go down to, let's say, get it down to 80 degrees Celsius, we would look at something like 380 millimeters of mercury. So what the takeaway of this, the takeaway is as pressure increases, so does boiling point. And so as you notice up here on the water line, once again, if we want to get water to boil at a higher temperature, we have to increase the pressure. And as our pressure decreases, the decrease in pressure, let's say like if we were to go up in the mountains and there's less pressure up there, then our boiling point is going to decrease, which is why it takes longer to cook things in the mountains, because the water doesn't get as hot. And if the water doesn't get as hot, it's like an oven at only 200 degrees Fahrenheit trying to cook a pizza versus an oven at 375 degrees Fahrenheit. It's going to take longer to cook, and that's really what's going on there. That's tonight's talk about properties of liquids, and a little bit of phase changes, and a little bit of boiling points and how they relate to pressure and vapor pressure. Have a nice evening.